this is the right way to look at them. And to be more specific, these are the A Cauchy-Riemann equations, sometimes called the generalized Cauchy-Riemann equations. Because these are good for complex numbers, or hyperbolic numbers, or three hyperbolic numbers, or dual numbers. Or you go on down the list of algebras you haven't heard of yet, as long as they're associative and real, which is not that much of a restriction. This is true for complex. So like in the complex variables, we have this: partial f, partial y is equal to partial f, partial x times I. That is uy plus I vy is equal to ux plus I vx times I, which is minus vx plus I ux. You equate coefficients. Real part has to match real part. Imaginary part has to match imaginary part. Those are the Cauchy-Riemann equations I derived earlier today through much less interesting arguments. You're like, well, that's great. Well, there's more. In fact, I will leave the details out for you, but you can show that this continues to be true. If I calculate the, I don't know, let's say kth derivative of f with respect to partial x I1, partial x I2, partial x ik, then that is equal to the kth derivative of f with respect to the first coordinate times, if you'll forgive me, I'm going to start dropping the stars, vi1, vi2, vik. Partial differentiation with respect to the coordinates of an a-differentiable function can be turned into differentiation with respect to the first coordinate and an algebra multiplication. This is really, really cool. Let me show you why. You guys know I squared is equal to minus 1. Right? So I squared plus 1 is equal to 0. So I squared plus 1 times fxx is equal to 0, where f is a complex differentiable function. So fyy plus fxx is equal to 0. There you go. That's the Laplace equation. In hyperbolic numbers, we have the equation j squared equals to 1, which amounts to the equation 1 minus j squared. Oh, tell you what, let me just leave it j squared equals to 1. Multiply by a complex differentiable, hyperbolic differentiable function. fxx equals to fxx. But this means that fyy equals to fxx. If we let f equal to u plus jv, this means we have the equations uxx equals to that's all, folks. These are uyy, and vxx equals to vyy. You may not know it, but those are the one-dimensional wave equations. If you think of y as being time and x as being space, this says that the second partial derivative with respect to position is proportional to the second partial derivative with respect to time. These are wave equations. So components to hyperbolic differentiable functions are naturally solutions to the one-dimensional wave equations. Components to complex differentiable functions are naturally solution to the Laplace equation. Right? There's a whole theory of conformal mapping to allow you to solve various problems of Laplace's equation, like fluid flow around corners, by mapping complex differentiable functions from weird domains into that, from nice domains into that corner thing. So many things are known for this. So this is, to me, this is very interesting, because what I'm trying to get at is any equation in the algebra will be supported by a corresponding partial differentiation, partial derivative, partial PDE for the component functions of the functions which are differentiable over the algebra. That to me is beautiful. Now, a very hard question I have not yet answered in my research is if you give me a set of partial differential equations, right? Can you find an algebra which picks those up as sort of its Laplace equations? That's a standing question in my research. I don't know the answer to it. There are partial answers that have been given. There's a paper from 1952 by Ward where he answers the affirmative to first-order PDEs. He constructs an algebra which takes those first-order PDEs as the generalized Cauchy-Riemann equations for a set algebra of the appropriate size. But I'm interested in a much more general question than that. There's something I wanted to show you. Yes. So getting back to differential equations. So I'm just trying to show you guys enough so you can understand the beginnings of this. Now I want to show you, turning the page a little bit here. I'm not going to prove everything, okay? But I'm going to show you the next sort of, I mean, there's an integral. I have a way of defining an integral for functions over an algebra for any of these algebras. I have fundamental theorem of calculus part 1, part 2, Cauchy's integral theorem, a lot of like the loop stuff from calculus 3, that's all been done. I spent a semester or two with Daniel Fries. We've got convergence and divergence theorems for functions for series in the A calculus. Most of calculus 1, 2, and 3, and a good part of differential equations we've done by now. But this is what I'm really excited about, that we found this last summer. Not this summer, but summer before. This summer is when it finally made sense to me, really made sense to me. So here's the problem. Solve a polynomial and the differentiation operator acting on y equals to 0. So d would be like d dt, let's say. Which one did I do?
I was just asking about turning the I squared plus 1 fxx to f1y.
Oh, yeah, I'm using, so I squared,
Yes.
it's, well, it was here. Curses. There was, yeah. Okay, so we know what a polynomial is, right? It's something, suppose it's monic. So this would be something like, d to the, let's say, d to the n plus an minus 1, d to the n minus 1, plus da-da-da-da, plus, a2d squared, plus a1d, plus a naught. So this is my polynomial in the differentiation operator, which I'm using big D for, okay? So one of our central problems in differential equations is to do what? We want to solve this thing, right? Let me show you a method. So the thing I haven't, curses, there's something I failed to do so far. Before I can do that, I have to do a little groundwork. I was going to work it into the previous examples, but then I chickened out. Now I'm paying the price. So, complex numbers and hyperbolic numbers, there's another way to look at them. Complex numbers we can look at as polynomials in K mod the ideal generated by k squared plus 1. So what that is basically a plus bk such that k squared equals to minus 1. H we could look at as polynomials in some variable k mod k squared minus 1. And this works out to a plus bk such that k squared is equal to 1. So there's an obvious isomorphism to make, right? K is I and the other k is j. But in fact, you can do, this is a way to construct a whole bunch of algebras. Not every algebra can be constructed in this way, but many can. The three hyperbolics H3 is you just k cubed minus 1. So that's like a plus bk squared, such that k cubed is equal to 1. Fun fact, their matrices look like this. Anyway, I digress. So this is a way we can construct algebras. We take like all possible polynomials, and then we fix some, we impose some equation. And this is called taking a these are quotient spaces. This is a standard way to construct algebras. We cover it in Math 422 in a slightly less general context. But it's really not bad. It really isn't. Because the rule is, it's very simple, Travis. Whatever I take, I divide by whatever I'm putting here, that becomes the 0 in this space. And so if I have like something squared, everything higher than this gets collapsed by this relation to terms of this form. And that's all there is to it. Basically, you just operate like normal, subject to this condition. Add and multiply like normal, subject to that condition. Which is all I said to define hyperbolic numbers over there anyway. Okay? All right. So, here's what I go. Definition. The characteristic algebra to star. Star is this differential equation up here, okay? This is what we call nth order constant coefficient ODE. This is a standard problem of the differential equations course, right, Travis? You can attest to this, right? We spent like 2 weeks solving that, right?
Yeah.
Yeah. Annihilators, all that good stuff. Tori, did you take DiffyQ? Okay, so, but you know, I mean, you remember the characteristic equation, all that stuff, right? So the characteristic algebra to star, check it out. It's just this. I'm going to call it I'll call it A prime. And what it's going to be is just R of K mod P of K. So it's the algebra in which we set the characteristic polynomial to 0. So what that looks like is, like A1 plus A2K plus plus AN minus 1 K to the N minus 1, such that P of K is 0. Where P of K is just, you take this and replace the D's with K's. We're good on that, guys? I think everybody in here has seen that before. Yeah.
Should that up in the top right, should that be A plus BK plus K squared?
Thanks, Sam. And minus 1. The thing is, this allows us to say, so essentially in here, we have that k to the n, all right, is equal to minus an minus 1, k to the n minus 1, minus minus a2, k squared, minus a1k, minus a naught. I mean, this is the condition that we get in the characteristic algebra to simplify things. Yeah? Yeah, I'm keeping it real for the moment. Oh, that's a good question. Yes, I did mean for these to be real coefficients. So to be precise, this is an element of the polynomials in the differentiation operator with coefficients in R. All of that is wrapped into saying this, real coefficients. All right. We can construct, so if you look at e to the kt, all right, this, if we look at t, maps to e to the kt. This is a function from the reals to the algebra A. I haven't actually told you how to differentiate such a thing. But it turns out you differentiate component by component. And the definition of an A-differentiable map of that nature is just that each component function is separately A-differentiable. Let me not get into all that. So this is going to be, so how do I define that? That's just the sum, you know, n equals 0 to, or maybe different letter, something I haven't used yet. P. I think I used P. Q. Q equals 0 to infinity. Sorry, I'm an idiot. Kt to the q over q factorial, right? This is how I define the exponential. And if you read the paper by Daniel and by Nathan, papers, all of the standard properties have been derived. But this is also taking its values in A, which means you can write this as like u1 plus u2k plus u3k squared plus da 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 plus un k to the n minus 1. The theorem is this. u1, u2, da 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 da, un form fundamental solution set to star. In other words, I can calculate the solution to any constant coefficient differential equation by simply calculating the exponential in the characteristic algebra and selecting component functions. That solves everything. Let me show you. There are 3 cases. I'll keep it quadratic. Hopefully I have time. Phew. I was worried there for a second. What example am I on? I don't know what example I'm on. Example 4, that's it? Man, I feel like I've let you guys down. Let's see here. So how about this? Y prime equals to 0. We'll start out with that. This one's really easy. So here we're looking, the P of k is what? It's just k cubed. So our algebra, what is it? The extension algebra is very simple. It's things of the form a plus bk plus bk squared, and that's it. I did it again. It's amazing I can speak at all at this point, though, honestly. So, check it out. E to the tk. Now, this one we can actually just straight up calculate. This is really nice algebra. 1 plus tk plus 1/2 t squared k squared, and then what? 1 over 3 factorial, right? T cubed, k cubed. Oh, k cubed is gone. Is no more. So, identify u1 is 1, u2, t, u3, 1/2 t squared. These, fundamental solution set. Of course, you can get this by just integrating 3 times, just the same, right? But there it is. I mean, y is equal to c1 plus c2t plus c3 t squared over 2. That's the general solution to that differential equation by this method. Oh, fine. I can integrate 3 times too. Yay, big deal. Let's try something a little bit harder. How about, what do you guys want?
Any differential?
Yeah, a second order. How about complex case, right? Let's try, since my time is limited, I'll keep it relatively simple. y prime prime plus y equals to 0. So this time my a is a plus bk such that k squared plus 1 equal to 0. Complex numbers. So e to the kt is what? Yeah, you're right. It's cosine of t plus k sine t. For all the usual reasons, because this comes from the fact that k squared is equal to minus 1, right? You look at the power series expansion of the exponential, you group all the terms with even powers of k, you get plus or minus 1 from those. All the odd powers simplify to plus or minus 1 times k. Those group together to give you cosine and k times sine. What do you know? C1 cosine t plus C2 sine t is, in fact, the general solution to that problem. In fact, this example is the whole motivation for the method. This is complexification taken to the extreme. This is okay, but this example is where this is where you realize that I got something here that's actually kind of neat. This is a repeated root. This is the one we have to multiply by t. Why do we multiply by t? Many reasons exist, right? So here we're looking at k squared plus 2k plus 1, aka k plus 1 squared equal to 0. Now this requires a little bit more ingenuity in terms of my calculation of the extended exponential, but e to the kt is, of course, e to the k plus 1 t minus t. Yes, no? And then, properties of exponential. Thank you, Daniel Fries or Nathan Bedell, I forget which one. One of those guys. They did it. It's in the paper, I promise, it's there. Not peer-reviewed, but I mean, it's reviewed by me and them. It's probably it. I'd like somebody else to look at it. I really need to submit those for publication somewhere. Oh well. Anyway, so this is, but you know, what can I do? I got to teach my calculus. So 1 plus k plus 1t, and then plus 1/2 k plus 1. Oh no, how embarrassing. I wrote k plus 1 squared because we know it's 0. As is everything else above. Lo and behold, you got yourself e to the minus t times 1 plus t plus kt e to the minus t. So this gives me fundamental solution set e to the minus t 1 plus t and t e to the minus 2. I'm sorry. Yeah, and t e to the minus t. Now that's a little bit non-standard, but you can easily see that if you subtract the second one from the first one, you get a naked exponential and t to the minus t, which is the usual fundamental solution set. So it ain't always pretty, but it's always right. I've proved it in general, that you'll always get a linearly independent set of functions that solve the differential equation. So I use the same technique to solve, you know, the repeated root. And this also worked for distinct real case. I mean, we can work that out too. Try it out. It's fun. But, you know, that's not the reason I did this. The reason I did this was, yeah.
What if it's equal to another function? It's not equal to 0.
Well, I haven't studied that yet. But I have theorems which suggest, I mean, I'm pretty sure I know what the fundamental solution. I think that the usual theory of linear ODE still holds. As you know, the basic thing is to construct the fundamental solution set and then pass that particular solutions. But I think I've worked out variation of parameters that works over in algebra. Yeah, but I don't have a lot of examples yet. Here's the thing, guys, though. If we have a polynomial in let's say dd zeta, it's my usual notation for an algebra derivative, zz zeta. If this is an element of the polynomials of differentiation over the algebra, So dd zeta is just my notation for, I can't draw zeta worth anything. So here I mean differentiation on A. It's the derivative I defined, like the f prime of p. Okay, that derivative. If I have a polynomial with coefficients in the algebra, in other words, a constant coefficient differential equation with coefficients in the algebra, exactly the same calculation still works. And this allows me to solve arbitrary constant coefficient differential equations with coefficients from any real associative algebra, finite dimensional. I don't know if I need commutative or not. I might need commutative. I don't know. Anyway, I've been working with this stuff for about 4 years, so I've learned a few things, but there are many open questions that remain, and so anyway, maybe some of you will work with me on those. Okay, so next time I'll get back to behaving. All right, today I was misbehaving. You may have noticed. And so next time we'll go into inverse and implicit function theorems, where we'll shnikes. One thing I was going to show you today. Oh, no, that's a good thing to show you next time. Next time I'll show you why. I'll try to start. Remind me if I don't do this. Stop me. Next time I mean to show you. In calculus 3, we do this thing where if we have the Jacobian of the inverse, it's 1 over the Jacobian of the forward transformation. Like if you want to write x as a function of UVW versus UVW as a function of XYZ, then the Jacobian of one way or the other, they're reciprocal to each other. Jacobian means the determinant of our Jacobian matrix in Calc 3 usually. We can prove that carefully in here without a lot of work. And I think that would be something good for us to do, to try to connect with Calculus 3 a little better start next time. And then we'll dive straight into the question of like, how do you partial differentiate? Suppose you got a bunch of equations, and you want to solve those system of equations for one variable in terms of the others. The implicit function theorem gives you a clear answer to when you can do that. Well, that's too strong. It tells you a nice condition that tells you that you can do it. It doesn't say categorically that if that condition is not met, you can't do it. That's kind of the nature. I mean, there are always weirdo cases where you can still do it despite the conditions of the theorem not being met. You know how math is. And then also the inverse function theorem, which says, you know, when can you find an inverse function? And both of these questions are beautifully and concisely answered by Jacobian matrices. And it's really, really simple. But the problems it allows you to tackle are really complicated. So it's cool. All right, I shut up. Have a good weekend, you guys.